Hello everyone, I am Saeed Al-Abri from the Georgia Tech System Research Lab at the Georgia Institute of Technology. Today I will talk about a derivative-free optimization method with application to functions with exploding and vanishing gradients. This work is in collaboration with my colleague Tony Lin, Professor Mulay Tao, and my supervisor, Professor Fiumin Zhang, all from the Georgia Institute of Technology. The problem we consider in our paper is as follows. Suppose we have a scalar function z in d dimension, and we want to find x star where the function z has a minimum. We consider two main challenges. The first challenge is, first, the z function or the analytical forms of the z functions and its derivatives such as the gradients or the Hessians are all unknown. So using, for example, a gradient descent algorithm or Newton method do not apply. Second, the function z possibly suffers from exploding or vanishing gradient problem. Here on the left, we show an example of a function with exploding gradient where the gradient changes dramatically from one location to another. So using a gradient descent algorithm, for example, might suffer stability issues. On the right here, we show an example of a function with vanishing gradient where the minimum is located along a long valley of vanishing gradients. So using a gradient descent, for example, here will be extremely slow. Derivative-free optimization algorithms nowadays are very important, mainly for the following reasons. One, many systems have only black box models without analytical forms. Second, gradient estimation can be impractical due to noisy returns as in reinforcement learning, or impossible due to exploding gradients as in deep learning. Third, extending gradient method to non-smooth cases is non-trivial and cannot be formulated through partial derivatives. In contrast, our proposed method does not rely on gradient estimation, is robust against vanishing or exploding gradient, and finally has search dynamics that can be used for theoretical analysis. Here we illustrate the basic idea of the SUSD optimization. Suppose we have a scalar function in 2 dimensions, and the function has a minimum somewhere here. According to the SUSD optimization algorithm, we construct a swarm of virtual agents, and each agent is located at the location xi. Then we modulate the velocity of each agent according to this dynamics. So the velocity of agent I will be a constant gamma times z at xi, which is the function evaluation, along a direction motion or along a motion direction v1, which is based on the spatial distribution of the agents. So for the spatial distribution of these agents here, we can use the principal component analysis to determine the direction of the largest variance and the direction of the smallest variance. And then we can compute the eigenvector of this covariance matrix here to determine v1, which is a unit length along the direction of the smallest variance, and v2, which is a unit length vector along the direction of the largest variance. So v1 will be the eigenvector of the covariance matrix C corresponding to the smallest eigenvalue of C. So the idea is that for all agents will speed up or slow down, hence the name SUSD, based on their current function evaluation at their current locations, and they will speed up or slow down all along the same direction v1. This v1 what we call the SUSD direction. So in the animation here, we show these red arrows here represent the SUSD direction, v1. However, the length of the SUSD direction is scaled by the function evaluation. So the agent here on the back has a longer arrow compared to the agent here in the front because its function evaluation is much larger, which means that this agent here will speed up much faster than the agents here in the front. As we run the animation, we can see that the agents will speed up and slow down. And this speeding up and slowing down behavior distorts the spatial shape in a way that forces the SUSD direction to align with the gradient direction. And eventually, the swarm reaches to the minimum of the function. A novel contribution we have in our paper is what we call the exponential mapping. And this in particular is to handle the exploding and vanishing gradient problem. So the basic idea is instead of speeding up or slowing down directly based on the original function z, we map that function by a map f. And we define this map according to this equation here. So f at z equals 1 minus the exponential of z bar minus z at xi, where z at xi is the original function evaluation, while z bar is the instantaneous minimum among the agents. And the main properties of this map is first, it maps the z values from 0 to infinity to a range of 0 to 1. So even if the function explodes, still the agents will speed based on a range between 0 and 1, which is a reasonable speed. And the reason why this work for SUSD, because SUSD does not depend directly on the intensity of the function evaluation. It depends more on the inter-eigen differences of the function evaluations among the eigens. And the second property, Z bar is decreasing by design. That's why how we design it here. And this property is important, which allows us to design a termination policy. So for this example here, the gradient exploded here. However, using the exponential mapping, although initially the Z function is extremely large, like 2.5 to the power 10 of 6 in logarithmic scale, but still the swarm is able to align with the gradient direction and reach to the minimum. And as you can see, the trajectory of Z bar is decreasing. A significant property of the SUSD optimization is that we are able to obtain what we call the search dynamics or the optimization dynamics. This actually is in contrast to most existing derivative-free optimization algorithms, which they lack search dynamics. What we mean by the search dynamics is the dynamics of the measurement at the center and the dynamics of the SUSD direction. We actually obtain these dynamics for both mapping, the linear map and for the exponential map. And to explain what these dynamics mean, we show it, this is for any dimension, but in this slide, we show it for 2D, okay? So for a 2-dimension, the previous equation reduces to this equation. What does this mean? Using what we call the design dynamics, which basically mean this is what we do actually. So this is what we do, xi dot equal gamma times z along v1, where v1 is the BCA direction. However, for a continuously differentiable function, we can show that the dynamics of the SUSD direction is given by this equation here. And if you pay careful attention to this equation, this is a consensus on a sphere between the SUSD direction and the gradient direction, plus some higher order terms, which we don't ignore in the paper. We still consider the higher order terms in our convergence analysis. So the main insight here is, although the knowledge of the gradient is not required, SUSD implicitly works as a gradient descent on a sphere. And this is what we mean by the gradient descent on a sphere, which is a very remarkable result, because that's what we have. That's what's happening implicitly, although we don't require the knowledge of the gradient here as we run the algorithm. In our paper, also we obtain a convergence result, and this result is we show that the SUSD direction align with the gradient direction n. So this n is the unit length direction of the gradient. So in order to show this, we come up with a variable theta equal 1 plus the inner product. So theta equals 0 if the SUSD direction is along the negative direction of the gradient. And then we derive the dynamics of theta, which equal a component that depends on the linear part or the gradient, plus some higher order terms delta. We use input to state stability analysis, where we view the higher order terms of the field shown here in delta as a noise or as an input noise. And then we have a theorem showing that our SUSD direction actually align with the gradient. So basically this is this sketch illustrates this idea. So suppose we have a function with 2 minimums. So in all of these blues areas, according to our convergence results, the SUSD direction V1 will align with the negative direction of the gradient until it reaches a neighborhood around the minima. And we actually derive that size of the neighborhood mu, which actually depends on the eigenvectors, eigenvalues of the spatial shape. It depends on the dimension and depends on the higher order terms of the field. In our paper, we derive several simulation results to demonstrate the efficiency of our algorithm. We first demonstrate the efficiency of algorithm for exploding gradient functions. And in particular, we simulated for the linear quadratic regulator cost function. So for this linear system, this is the linear quadratic cost function. And it's known that this cost function is non-convex. And more actually, if the system is unstable, then the cost function could explode. A significant results of our SUSD algorithm, we don't require an initial stable cost function. And as you can see here in the simulation, this is for the 2D cost function. Although the cost function initially is extremely large, but the SUSD is able to converge. And here we try it for different number of eigens. On the right here, we show the cost function for this system. So the dimension here is, of the cost function is 12. So it's in R12. And we compare our algorithm to the natural policy gradient, which is recently get more attention. So as you can see here, SUSD is able to converge much faster than the natural policy gradient, which oscillates and takes more time. We also, to demonstrate the efficiency of the algorithm for a vanishing gradient problem, we simulated for the Rosenberg function. And actually, we added also some noise to show the efficiency of the algorithm. And as you can see here, by various level of the noise, SUST is still able to converge within a reasonable amount or number of iterations. We also simulated for many other functions, which is not in the paper, but this is as an ongoing research. So here, for example, for a 50-dimensional function, for the quadratic function, or this for the Ackley function, which has like an infinite number of minimum values, and also this is for the Gruic function. And as you can see in all of these, this is in 50 dimension, and still we are able to reduce the errors in a reasonable amount of iterations. As an ongoing research, we are currently actually extending our research by using multiple swarms for faster convergence. We are also running SUSD on random subspaces for extremely high dimensions. We're also integrating SUSD with Bayesian optimization to make it a global optimization solver. And finally, we develop a distributed SUSD derivative-free algorithm. With that, I conclude my presentation, and I want to acknowledge the sponsors and some of the undergrad students who helped me running some of these simulations. I will be happy to answer any of your questions. Thank you for listening.